All right, so good afternoon, everyone. Welcome back to our second chemistry lesson. I hope everyone's doing well during this cell isolation time. All right, so without any further ado, let's get started with our lesson. Okay, so for our lesson, we are going to we first start with the scientific method. We look at the unit of measurement and also the uncertainty in the measurement. All right, so let's have a recap before we move on. So for the unit of measurement, because it's very important, we have to know the what kind of measurement we're going to measure. For example, we're going to measure temperature. So for example, we have 10 degree. We also have to know the unit. So for different units, we have to know the SI unit. So we have a standardized unit for us to use in chemistry or in science. So for different parameter quantity so stuff we have to use different SI unit for measuring them. All right, so yeah, it's pretty straightforward. For instance, for temperature, instead of degrees Celsius, you use Kelvin, and then the length will be meters, etc. So there will be a different table you can have a look on that. Okay, second, for the uncertainty measurement. So I mean, again, in chemistry, it's a practical science. So we have to do a lot of measurement. So when we are doing measurement, we have different value number, something like that. So for instance, we measure the length of a pen, then we will have a distance. We measure the temperature. We have the temperature. But again, we don't know the exact length and also the temperature because there will be uncertainty. For instance, on your ruler, there are different marking. So on the marking, they will be different a little bit. Sometimes you can measure up to 0.5 centimeters. Sometimes you can measure it down to 0.5 millimeters. So it will depend on the technique that you use. All right. So for the uncertainty in measurement, we can represent with accuracy, and also precision. So we have two different things. So if you remember, accuracy will be depends on the measure value. What will be, is it close to the reference value or the true value? And second, the precision, how far for each measurement are different from each other. So in order to summarize that, actually for accuracy, we most of the time we are going to use a percentage to see the difference between the real value or the reference value and your measure value. And the precisions are always hidden in the uncertainty when you represent your measurement or something like that. For instance, you measure the length of the pen, say for 5 times, and then you find that the average is around 10, and then for each measurement is deviate for 0.5. So 10 plus or minus 0.5 millimeters or centimeters. So the precision is represented by the spread in your result in the average. So that's I remember that's where we stopped from last time. All right, so when we move on to the third topic, it will be our significant figures and also calculations. Significant figures and calculations. All right, first of all, what is a significant figures? So for significant figures, we are going to represent our number in different. We can represent our number different way. For instance, we can say we can have say I have a 15. You can show it as 15.00, 0.15, or 1.5 times 10 to the power of 1, something like that. So we have different way to represent that. But yeah, among each of the way to represent our data, they will have different significant figures. From here, actually, it will tell us how much information our measurement contain. For instance, if we're going to measure the weight of an object, so we can have two different balances. We can have a balance that you can find in your kitchen, say they will give you up to 1 gram. So when you measure something actually is 15 grams, for example, you have a lot of a bunch of sugar, so it's 15 grams of sugar. So you use your kitchen, you use your kitchen balance, and you find that's 15 grams of sugar. Okay, and then you are going to bring that same amount of sugar back to your lab, and then use the analytical balance. Analytical balance is much more it can provide much more information because it can tell you the weight down to 4 to 5 decimal place. So say you actually measure is 15.0001 gram from your analytical balance from your for your sugar from the analytical balance. All right, so from here we can see that this is from your kitchen balance, and this is from your analytical balance in your lab. So you can see that 2 different balance, they can give you different amounts of information. For your kitchen balance, it only can go down to the 5. I mean, just before the decimal place, to the single digit over there. But for analytical balance, it can go beyond the decimal places 1, 2, 3, and 4 decimal place. So give you much more information. You will know whether you have 15.005 or you have 15.5001 by using the analytical balance. But for the kitchen balance, they only can give you 15 gram. So it can be 15.6, it can be 15.2, it can be 15.1, etc. So you just don't have this information over here. This information over here. So that's why when we are going to represent our results, we're going to use significant figure to represent how much information we have for each measurement. Okay, so again, because the purpose of using significant figures is to show how much information, the first thing that we have to know is to count the significant figures. All right, so we have to learn how to count that. So first of all, for long 0 digit, they are always count as a significant figures. For instance, we have 15, so we have 1 significant figures, 2 significant figures. So 15 we have 2 for this case. Okay, but for 0, it will be a little bit complicated because we have a leading 0, and also we have a captive 0, and also we have trailing 0. So for leading 0, for instance, we will be 0.15. So the leading 0 over here, they don't count as significant figures. They don't count as significant figures. How about captive 0? So for example, we have 0.1501. The captive 0 will be the 0 between 2 actual long 0 number. So from here, actually, they are going to be counted as a significant digit. Okay, for trailing 0, for this case, we go back to our 15.00. Okay, so when the leading way end of the number, it would depend on the decimal point. All right, so if we have 15,000, that just before decimal point, they doesn't count as a significant digit or figures. But if they are behind the decimal place, they actually count as that. Okay, so sometimes we have an exact number. For example, they have a constant. They can be a constant. They can be just a finite number. For example, we have 1 apple, 2 apple, 3 apple. We can say 1.5 apple, but it's really rare to say it's 1.5 apples. So for those that have a finite number or exact number, they have a infinite number of significant figures. So just keep in mind of that. But again, most time when we are doing measurement, for instance, we are going to do a titration. We want to find out the volume. Say we have 35.1 mil. All of the time we have a significant figure associated with that. Okay, so we can move on. Okay, so for another thing, we have to know how to count that. We have to represent our result is that we are going to use exponent. For instance, we have 2 to the power 4, something like that, 5 to the power of 5, and then we have n to the power of x, so we have a to the power of n. So sometimes we just want to represent, just multiply for a couple of times, so we're going to represent like that as an exponent. Okay, so okay, so yeah, let's keep moving. All right, so the first exercise we are going to look at is that we're going to count the significant figure for all three different number over here. So we can have a review, so we can know how much number we have. All right, so for the first one, we have 0.0077, 0.007. Okay, so what would be the significant figures? So from here, actually we have two, because we have actually three. 0.0077, three leading zero, and they don't count as significant figures. So, and we have two non-zero digits, and we have 1 and 2, so we have two significant figures, or significant digits. Okay, so for B, 2.008, well, how many of them? So we have one non-zero, we have two captive zero. They are also counted as significant figures, and also they have 8, so we have 4. So we have four significant figures for 2.008. Okay, so how about 100? 100. Actually, it's pretty tricky, I would say. But if we consider we actually is a measurement, for example, for the mass of a particular system is 100 gram. Then from here we should have three um, significant figures, because from here we have assume 100 gram. So we have 101, because you think about that. It can be 101, 102, because it's 100. So you still have information about this digit over here. So you can 101, 102, 103. Then it will be three significant figures. Because when you change the numbers, actually, yeah, it means something there. All right. So, but it also can be a whole number. For example, 100 apple, 100 pen, 100 molecule. Then for this situation, actually, we have an indefinite amount or infinite amount of significant figures. So we have so many, we just don't know. It's 100 apple. It depends what we are measuring. And also at the same time, if the 100 is a constant, it's just a factor, it's a constant that we're going to multiply. Again, it just have an infinite number of significant digits. So actually, for 100 here, it's kind of tricky. It really depends on the situation. So if your actual measurement, that is a number that means something. For example, the weight, and up to here, it gives you information at the lowest value. Then we have three significant figures. But it's just a number of something that cannot be separated in half. It's just a whole number. Then we have an indefinite number or infinite number, and also same if it's a constant. So I hope you should be careful about that. All right, so let's move on. All right, so yeah, sometimes we have some large number, and we want to represent that in an exponential form. You just make our life a little bit easier. But again, it depends what you want to do. But you don't always do that. For instance, we want to express 64 in the exponential form. So 64, you can imagine, okay, what number can be multiplied by itself for so many times to get 64? Essentially, it would be 2. It would be 2. So yes, we are going to write as 2 to the power of 6, because we multiply 2 by 6 times, and then it will have 64. And then for second example, with 256, it will be 2 to the power of 8. Yeah, so it is useful, but it will depend on the situation. So depend what kind of experiment you're doing and what's your purpose to represent the data in terms of exponential form. Okay, so first of all, we learned that the significant figures. The significant figures is a way that we represent our measurement to tell people how much information in there. For instance, we have 100 gram of weight, where we have 100 milliliters of substance, and then we have 0.015 mole of our molecule or solute in a solution. However, all of the time when we do experiment, we have to do some mathematical analysis or operation in order to find out our result, our purpose, or just a number, or just the answer of a particular questions. Okay, so from here we have to do mathematical operation. So how can we combine different measurement with different significant figures, different amount of information, and then at the end of our result, we still have the we can show the result with the appropriate amount of information present. So that's why we're going to learn what kind of mathematical operation we are going to how to um, how to process the significant figures. Okay, so all right, so we have how many mathematical operations do we have? I believe we only have. I mean, generally we have four, but overall we only have two. Yeah, overall we have two. So we have addition and subtraction. We have multiplication and also division. Yeah, but you can think about it as four, or you can think about it majorly. So it's two. Okay, so we have two different types, but we use a different approach and different method to handle the significant figures. To handle the significant figures. So first of all, yeah, a lot of time we do. Let's start with multiplication and division. Most of the time, when we want to find out the concentration, we have a number of moles divided by the total volume, for example, so for 1 liter, and then we can find out the concentration. So we can have the yeah, we can do as multiplication and division first. Okay, so for here, the rule of thumb is that, or the general rule is that when we are going to do subtraction, or not subtraction, multiplication and division, we are going to take the least, or keep the least significant figures. Keep the least significant figures. For addition and subtraction, we are going to keep the least decimal place. Decimal place. All right, so multiplication, division, we keep the least significant figures. Addition, subtraction, we keep the least decimal place. Decimal place, significant figures. All right, so we can move on. Okay, so first of all, we have to identify what kind of mathematical operation we are going to do, and also the order, the priority. And then we are going to look at whether we are going to keep the least significant digit, or we are going to keep the least significant figures. Sorry about that. All right, so first of all, for A, we have multiplications is 4.56 times 10 to the it's times 1.4. Okay, so it's a multiplication, so we're going to keep the least significant figures. Alright, so on the left we have 3 because 1 over here, 2 over here, 3 over here. On the way 1.4 we have 2 significant figures. Significant figures. Alright, so it's significant figures. Okay, so we can just multiply them as usual. So 4.56 times 1.4, you can use a calculator, and you should be able to find that as 6.384 by using your calculator. Okay, however, again, we have two different measurements, and they have two different amounts of information. Two different amounts of information. When you have something with a lot more information, going to combine with the other one with less information, then your result should have less information because it's limited by the measurement that had the least amounts of information. Okay, so therefore for this case, we have 3, we have 2, we're going to choose 2 significant figures for our result because it's limited by the least amount of information that limited by the measurement that with the least amount of information. So therefore we have to convert this guy into 2 significant figures. So it will be 6.4. We can start counting 1, 2, 3, 4 significant figures. We only want to keep the first 2. We are going to round up we have 8, so we are going to round up the second number over here. So that's why we have 6.4 as for our answers. And we will talk about the rounding up later. Okay, so this is a pretty easy operation, but from here you can see that the reason that we chose the least number of significant figures because our answers or our result is limited by the information provided by the Yeah, by 1.4, because 1.4 had the least amount of information. All right, so we go back to B. So to B, we have 11.11 plus 18 plus 1.013, etc. All right, so we have addition subtraction. We are going to keep the least decimal place. Least decimal place. So again, from here, the difference between them is the number or decimal place. But when we have a high number or decimal place, it will give you a lot more information. So when we add together, we're going to choose the one with the least decimal place, and then we are going to find out um, our answer and choose the one with the least decimal place. Again, the same reason, because they are different amount of information, and also due to the limit that information, we have to represent our result in such a way to show that we have a result that have a limited information. Okay, so we can just proceed to just add everything together. So when we add everything together, we will find that the answer is equal to 31.123 over here. And then we are going to find out what will be the least decimal place. What one will be the least decimal place. So when we look at all three numbers, we should be able to find that 80.0 had the least decimal place. Okay, so and the decimal place number is 1. Because we have 80.0 and we only have one decimal place over here. So from our result over here, we only can show that the decimal place to be only one decimal place. So we are going to discard everything behind that. So again, because we have 2 behind the 0.1 over there, so 2 is less than 5, so we don't have to do any round up. So instead of showing the answer as 31.123, we're going to show the answer as 31.1. Okay, so it's not that difficult. Okay, so we can keep moving on. All right, so again, when we have to say, for example, when you use your calculator, you find that you have a lot of decimal place, or you have a lot of much more significant figures, and then we have to cut it off. But when you cut it off, we also have to do some rounding up. So for the rounding up, there's a rule. So when it's less than 5, then we just keep the number the same. When it's equal and larger than 5, we are going to increase by 1. For instance, for 1.28, for example, we only want to keep one decimal place. That will be 1.3, because we want to keep this one over here, but the one behind that is larger than 5, so we're going to wind up. We're going to wind up. All right. So and then when we have so for example 3.22, we want to keep 2 significant figures. Then the number that just behind the second significant figure over there is 2. So it's less than 5. So we're going to, when we present our answers, we're going to keep it the last one as 2. Yeah, just doesn't change it. So so it's not that difficult. It's that simple. Okay. Another exercise again. Okay, so we want to okay, from here, although the question asks you to write out the answers, but I would prefer also taking consideration of the significant figures and decimal place. So first of all, A, we have 107.8 plus 0.35, and then also plus 0.195. So 107.8 plus 0.35 plus 0.195. I don't like the way that again your the look you show it here to show the 0 over here. The reason is that because from your measurement it only tell you 107.8. They only tell you the information up to one decimal place. If you add 2 there, do you mean that you somehow know the number behind 0.8? You have much more information? I don't think so. So this is not a good way to represent your measurement or your result. So we have to keep in mind that when you put a 0 over there, okay, is it actually it actually makes sense because it's just the limit of your equipment that cannot tell you much information. All right, so okay, let's keep moving. So when we just add everything together, we happen to find that's 108.345 gram, but we don't consider any significant figures or decimal place. Okay, and then we consider this decimal place. Again, yeah, we have one decimal place because we addition. We only consider this decimal place, so we only have one. So we have 108.3 gram. 108.3 gram. Okay, so when over here, yeah, I keep that 3 because the number behind is 4. It's not equal to 5. It's less than 5, so that's why we don't have to change it. We don't have to change it. Okay, so we move on to the second question. We have 249 times 0.3 centimeters. So 249 times 0.3, 0. Again, we use a calculator to find out the answers. And then you should be able to find it at 74.7. So 74.7. Alright, so yeah, use a calculator to find out this number. And then we're going to look at significant figures, how they change. So we have 1, 2, 3, 4, 2 for 39, so we have 3. And then 0.30. Yeah, so training 0 also considered as a significant figure, so we have 2. So we have 3 significant figures times 2 significant figures. For multiplication, we choose the least amount of significant figures, so we're going to keep it at 2. From your calculator, 74.7. So it's limited by 2, so we're going to keep the first 2 over here. But again, the third one is 7 is higher than 5, so we're going to make this. We are going to round it up to, instead of 74, we have 75. So the wind up and also the handling of the significant figures and decimal place is that easy. It's not that difficult. Okay, more question. So okay, let's practice again. So for the first one, how many significant figures? So we have 5 non-zero number, so we have 5 significant figures. Yeah. And then for the B, we have 3 non-zero. Yeah, so we have 3 significant figures. The leading 0 doesn't count. Yeah, doesn't count. Okay, we have 0.2. Again, we have 1 non-zero, so we have 1 over here. Let me erase that. Yeah. Okay, so we have 107.0. We have 2 numbers, non-zero number, 1 zero sandwich between 2 non-zero number, and also a training 0. So yeah, this is also counted as 1, 2, 3, and 4. So we have 4 significant figures. Yeah, so it's not that difficult. All right, so we're going to subtract the measurement and then we write our answer. So we have 25.35 milliliter, and then we have 20.5 milliliter. Okay, so first of all, I just don't think about the significant figures or the decimal place. I just use my calculator to find out the answers. So I'm using my calculator to find out the answers, and then it will be 4.85. Okay, and then going to look at the significant figures or the decimal place. Alright, so we are going to do a subtraction. So subtraction, we are looking at the least decimal place. So we have 2 over here, we have 1 over here. So therefore, for my answer, I should only have 1 decimal place. So I should have 4.8. At the same time, looking at the number behind the 0.8 over there, it's 5. So when it is 5 or larger than 5, we have to round up. So the answer will be 4.9. Alright. Okay, so in the experiment, the span of time is determined to be 8.050 times 10 to the negative 3. Find the number of significant figures. So 5 times 10 to the negative 3. Okay, so how many non-zero digits? We have 1 and 2. And how many leading 0? We have 0, so we don't have to think about that. How many zeros sandwiched between 2 numbers? We have 1 over there, so we have the third. How many trailing 0 or 0 at the back? We have 1. So from here, actually, we have 4 significant figures. Yeah, because we have 2 non-zero number, 1 0 sandwiched between 2 non-zero number, and so also 1 0 is behind the 1 0 is behind the one of the non-zero number, and also it's a trailing zero. Okay, so question 4, we want to simplify 2 times 2 times 2 times 2. So we just use exponential form. So we have 2 to the power 4. And then we have 1.5 times 10 to the power of 5. We present 1.5 times 10 to the power of 5. Oh, actually, I don't really know what they want to show here, because for 1.5 times 10 to the power of 5, we use something called a scientific notation. It's a short form to showing a really large number. And I believe it's a really good representation when you're actually doing, experiment and also in chemistry. Okay, so we can move on to question 5. We calculate the volume of box when measuring the correct number of significant figures with the width, length, height of a small ball is 17.1 centimeters, 29 centimeters, and 6.2 centimeters respectively. Okay, again, before I do any significant figures analysis, I will just find out the answers. But again, it's very important. Find out the answers. Significant figures is only part of the answers. But okay, let's find out the answers. So how to find volume? First of all, for volume, we have our width times our length times our height. See if I can draw a box. Yeah, my drawing is really bad. Okay. I hope you can see that it's a box over here. Yeah, hopefully it's a box. All right, so we have the height, the length, and the width. So we just multiply all three together. We know the whole volume of the box. Okay, so we just need to have 17.1 times 29 times 20.6.2. Yeah, don't miss out the units. Yeah, I'm not a really good example. Don't miss out the units. And then I'll use my magical calculator to find out the answers. So 17.1 times 29, 26.2. It's a pretty long number, so it's a 3074.58 centimeter cube. Okay, so first step, I have the answer. Second, I'm going to do look at the significant figures. Okay, so from here you can see that for the width for the box is 17.1. So somehow you have a much more accurate measure. I would say you have a much more I don't know, high tech, maybe much more better ruler to measure the width, because you know that is 17.1. Or maybe use the same ruler that you measure for the height. But yeah, you have 17.1, and then when you measure the length, somehow you use a different ruler, and then you only can tell you down to maybe 1 centimeter, so 29 centimeters, and then for 6.2 centimeters for the height. Okay, so for the next step, we are going to look at the significant figures. Okay, first one, 17.1 will be 3 significant figures. We have 3 non-zero digits. 29, we have 2. I'm not talking about actually significant figures, if you're confused. So we have 3 for that, 2 for 29, and 2 for 6.2. When we are going to multiplication or division, we are going to choose the one with the least significant figures. Yeah, so the 2 over here, yeah, because it's 3. Yeah, there's a much more information than the other 2, but we only have 2 for the list. So we are going to keep 2 significant figures. So from here, we are going to choose the first 2 significant figures from the left to the right. So of course will be 30, not 30, it's 3,000 or 30. Okay, so but we have to look at the third significant figures is 7. So at the end of the day, we will have 31,000 centigrade. 31,000 centigrade. Okay, if you remember the previous question, I didn't count properly. So I should start counting from the left to the right. So 1, 2, 3, and 4. Alright, so when go back to our question over here, it's 3100 or 3,100 centigrade. So it is 2 significant figures. Yeah, but some of you think that, wait a second. We have 0 over there. It is 4 significant figures. Yes, actually, it's kind of tricky. It would depend the way that how you represent your answers, and also the situation. Okay, so first of all, from here we are measuring volume. The volume can have um, a fraction, can be uh, it can be a non-whole number. Yeah, so it can be whole number, it can be not a whole number. So from here, yes. So from this case, we may need to consider to um, how to say that. So from here, it can be 4, it can be 2. And from here, you can see that you can claim that, yeah, because we have 2, the train 0 over there, because it's not, how to say that? From here, yeah, because it's just 0, it doesn't show anything. But from here, I cannot just leave 31 and then there's nothing behind that. So that doesn't make sense. So we can show it as 31,000. Yeah, so yeah, it may be correct, but it causes confusion. So the proper way to show it, the significant figures properly for this question instead of 31,000 is that, because again, it just cause confusion. It can be 4, it can be 2. The proper way is that we are going to use scientific notation. So we know that we have to run up to 3,100. So we use scientific notation. We can remove the 0 at the back, and then we can show the significant figure in the remaining number. Okay, because it's 1,000, so 1,000 is 10 to the power of 3. So that's why we have 3.1 times 10 to the power of 3 centimeter cube. And then for this one, it will be a much more good representation on the significant figure and also the amount of information retained in our answers. So yeah, when you're actually calculating the number of significant figures and also decimal place, you have to be careful. And then when you're presenting your result, you also have to be careful that you have to choose the way to represent your result that is not confusing. So it should be easy to be understand. There's no room of argument. So then you choose that method to present your result, and then you just you're good. Okay, so I believe we have much more question. Actually, it's the same. It's the same exercise. So we just go through. We just went through that. All right. Yeah. So exactly. So from here, instead of showing at 3,100, we're going to do scientific notation. I mean, if you can find a way to present your result, it's much more easy to be understood and much more certain, then it will be easier for your life, even for my life. Okay, so here's a summary. Again, significant figures and also the decimal place. I mean, here they didn't talk about the decimal place. So from here, so decimal place. Yeah, it will tell you about the degree of accuracy, the amount of information that you have. From here, it tells you that if you have the much more number provided, if you have much more information, your number, your measurement will be much more closer to the real value. Then that's why the significant figures will tell you the degree of accuracy. So that's what it means from the first sentence. Okay, so how can we calculate the significant figures? Alright, so first of all, for any leading zero, they don't count as significant figures. Leading zero, they don't count. Captain zero, they are counted. Train zero, they also are counted. Exact number, they also be counted. Sometimes, so I would say put a tick and it really sometimes depends on the situation. Sometimes, if you have a measurement that can be long whole number, that can actually the last zero provide you information, then you have to count that zero for exact number. If you have something is you just you have something that you need a whole number to count, for example 1 apple, 2 apple, then for that it will be an exact number. Then it will be infinite. And also, if you have a constant, also is an exact number, then also is infinite. So for the last one, it's kind of tricky. So you have to figure out whether your number, your measurement is it exact number? Is it something that cannot be a whole number? Then it would be an exact number. Is this just a measurement that just gives you a whole number? It's just a measurement, but it's a whole number. But the measurement that if you've uh, uh, I think you'll be using the example much more easier. So, oh yeah, so for your measurement, we have 100 apple. Yeah, so you just have I mean, you only have one apple, two apple. They must be an exact number. Then yeah, so you have an infinite amount of this significant figures. But if you measure the weight is 100 gram, so on your balance, so 100 gram, it also tell you that it's 100 gram. It's not 101 gram or 102 gram or 100 or 99 gram or something like that. So from here, you can also say that the zero they count as significant figures. So yeah, it really depends what you are actually measuring. Yeah, because here you only can have one or two apple, but for gram for mass, yeah, so you can have a half number. You can have a half number. For instance, if you have 1.0, yeah, something like that. All right, so I think that's it for the significant figures and calculations. So it's not that difficult because most of the time you will see when you do a measurement, you won't have a whole number, so or exact number, so you don't have to worry about that. Okay, so we are moving on to the fourth section. It will be the dimensional analysis. Okay, so yeah, we already went through the accuracy and the significant figures and the unit. Dimensional analysis will be pretty simple. Okay, so for dimensional analysis, we also limit as a factor label method or the unit factor method. It's a quantitative analysis that to convert unit from the same direction from the okay, convert unit from unit to another unit of the same dimension. What does it mean? The same dimension over here? Same dimension means they means the same thing. For example, length. We can use centimeters, meters, inches, centimeter, meters, inches. They are all talking about length, but they are just different unit. So dimension is length. Unit will be inches, centimeters. Okay, so first example is that we have our what would be the length in inches for a pin measure 2.64 centimeters in length be? All right, so from here, we want to convert centimeters to our inches. So from here, first of all, we need to know the conversion factors. Because we have to know for 1 inches what will be the centimeters, or for 1 centimeter what will be the inches. So all the time is given. So for 1 inches, that we show that here is equals to 2.54 centimeters. So we are going to multiply by conversion factors, and then we can convert that to our to the same length but with a different unit. Same length to different unit, and this process called dimensional analysis. Okay, it sounds kind of a little bit confusing, but let's go through the calculation step by step. Okay, so from our let me remove that. I need some space over here. From my conversion factors over here, we can visualize that it's just a ratio. So for every 2.54 centimeters is corresponding to 1 inches. So for each 2.54 centimeters, we have a ratio is 2.54 centimeters to 1 inches to 1 inches. So yeah, you can also convert the ratio in a fraction. So we have 2.54 centimeters to 1 inches. They mean the same thing. The left over here, draw arrow, and the right over here, they mean the same thing, but you just represent in different form. Personally, I prefer the run or write because it's a fraction, so you can proceed to how you do the correlation easier. Okay, but let's start with let's start with our conversion factors, and then we have our ratio. Okay, so from here we want to convert our 2.64 to inches. So we just want to ask the question is, if we had 2.64 centimeters, what would be the inches? What would be that? We just don't know. We don't know. We want to find out. Yeah. So from here we can see that 2.54 increases, and also the inches also be increases. And because they are in ratio, so the amounts of the factor of the centimeters going to be increased will be equals to the factor that's 1 centimeters. Oh, no, sorry, 1 inch is going to be increased. So yes, let's find out the increase in the factor from 2.54 to 2.64. So when we have 2.54 divided by 2.64 divided by 2.54, we should be able to observe this at roughly around 1.04 time increase, because again they are in ratio, so the length in inches also be increased by 1.04 time. So from here we can conclude that it will be corresponding to 1.04 inches. Yeah, 1.04 inches, because the increase, both of them, this conversion factor is in ratio. If we increase one side, the other side must increase, because when you do a ratio over here, imagine they are on a balance. So they are on a balance. So we have 2.54 and 1 is centimeters and 1 inches. If this side is going to increase, the other side must be equal to the increase to maintain the balance. So I would say this is called the ratio or balance method. Okay, so if you think that this is a little bit confusing, that's fine. We can move on to look at the fraction method. The fraction method. Okay, so let me use that. Okay, the fraction method is that from here, for every 2.54 centimeters is for 1 inches, right? So this is from our ratio. 2.54 to 1 inches. Okay, we want to convert 2.64 center to 1 to I don't know how many inches, right? Okay, therefore, we have to somehow rearrange our conversion factor or the ratio or the fraction, and then we are going to combine with our number over here, and then we will have our um, length in inches. Okay, again, 2.54 centimeter over 1 inches. This is given from our conversion factors, and they are always they are in ratio, so they will be always um, when you actually calculate the number 2.54 divided by 1, it's always 2.54. Because they are in ratio, then the ratio number, the actual number that you calculate from this ratio will be always the same. It will be always the same. That's the that's the special thing about the ratio. Okay, in other words, you can set up an equation that you have 2.64 centimeters. I just don't know how many inches, because both of them, when you actually calculate the number of this fraction or of this ratio, on both sides they must be equal. Because again, due to the conversion factor, we know that 2.5 equals to centimeters equals to 1 inches. So it cannot be violated because that's the conversion factor. So when you actually do the calculation, it must be equal. Okay. Alright, so from here you can set up an equation 2.54 to 1 inches equals to 2.64 to x inches. Essentially the same as the last method, but I just represent it as a fraction. If you solve this equation, you will see that x inches equals to 2.64 centimeters multiply. This is the x over here is multiply. 1 inches over 2.54 centimeters. And you can see that you can cross out the centimeters, only the inches remained, and then it's 2.64 divided by 2.54. And then we will have our answer as 1.03. Okay, so to recap, what I say over here, in order to do a unit conversion, first of all, we need our conversion factor. We are going to express our conversion factor as a ratio, and then convert this ratio to our fraction. Okay, so this is given, and then we're going to represent our uh, the number that we want to convert in a ratio also as a fraction. For this case, 2.64 centimeters, and also we don't know how many inches. And then we solve the equation, and then we are going to look at the unit, make sure they have the same unit on the left and the right, and then we will have our unit conversion done correctly. Same thing happen if we have, say we don't know how many centimeters, but we have 2.64 inches. The same thing apply here. You still can solve for that. Okay, so let's keep look at more example. First one, you want to order a bicycle with 35.5 inches frame, but the size in the catalog are given only in centimeter. What size should you order? Okay, so we have 35.5 inches, and the conversion factor is given is 1 inches to 2.54 centimeters. So we want to convert inches to centimeters, so we can know, okay, what would be the centimeters of our bicycle. So yeah, from here we know that it's 1 inches to 2.5. So we can set up the ratio as 1 inch to 2.5 centimeters, and this is our conversion factor, and also this is the ratio that won't be changing. And then on the right hand side, we just want to know 35.5 inches. So we are going to say, yeah, we know it's 35.5 inches. Pay attention, if you have the same unit, they should be on the same location on the fraction. So centimeter, for this case, because I make the ratio is 1 inches to centimeters, so centimeter will be the denominator. So that's why I have to make sure the centimeter will be in the denominator on the left and on the right. We just don't know how many of them, but we have 35.5. So that's why we are going to rearrange this equation, and then we should be able to find that we have 1 inches over 2.54 centimeter. Sorry, the other way around. So we have because we move the x over here to 2.4 and 1 inches over here. So we feed 35.5 inches over 22.54 centimeters, and sorry, multiply 2.54 centimeters. Uh, yeah, it's on the edge of the screen, but it's centimeters, and then over 1 inches. So from here, you can see that we can cancel out the unit, and the remaining unit will be centimeter here. Yeah, so left and right have the same unit, so we have the equation right. So from here, that's why we have 35.5, actually 35.5 times 2.54 divided by 1 inches. It's come from this equation over here. And then we have 19.42. Okay, so let's finish the last question of today. Okay, so the speed limit of many highway in the United States is 16 miles per hour. What would be this number be supposed in kilometer per hour? Okay, so I believe the solution here is extremely complicated. So yeah, but you're going to do the same calculation over again and again. So I will provide you the conversion factors. Is 1 mile equals to 1.61 kilometer. 1.61 kilometer. Okay, so we want to convert mile per hour to kilometer per hour. All right. And then because we have the same unit hour in there, so we just keep the hour the same. So in other words, the conversion factor of 1 mile is equal to 1.61 kilometer. In other words, if we have 1 miles per hour, it should also be 1.61 kilometer per hour. Yeah. So so this will be the conversion factor that we are interested. So yeah, we are going to set up our equational the ratio first. 1 miles per hour is corresponding to 1.61 kilometer per hour. All right, and assume the speed limit is 60 mile per hour. Should be mi over here. What would be the 1 kilometer per hour? All right, so we already set up the equation over here. Let's start with very easy. We are going to rearrange the equation and solve for it. So we just don't know how many kilometer per hour. We just move it here, you move it to here, and then 1.6 over here. I mean, just cross multiplication. So we're 60 mile per hour divided by 1 mile per hour times 1.61 kilometer per hour. And then, yeah, we should be able to find that is 96.52 kilometer per hour. Sorry, my bad. So, yeah, 1.61. 1.61. Okay, so if you don't have any question, I will record it at the end of the day.